So last time we left off with calculating the left approximation of the area underneath the curve y equals x squared from 0 to 1. I'll run through that calculation real quick, and then we'll do it from the right. But first, let's just see kind of what this looks like as a picture. So here's the graph y equals x squared from 0 to 1. So if I want to make n rectangles, can someone remind me how to make, what is the width of each rectangle? So for n rectangles, what's the width of each rectangle? If you want to approximate with n equal width rectangles, how wide should each of these rectangles be? Correct, 1 over n, because we have b minus a over n. It's 1 over n. Okay, now let's say here's a rectangle here. Let's call this xi and xi plus 1. Let's suppose this is some interval. Where do you draw your rectangle? So the rectangle is based on some height, or you're drawing a line up to the curve. If we're doing left approximation, which point do I pick in the interval xi to xi plus 1? Xi, yeah, that's the left point of the interval. So we're drawing a line up from xi to the curve, and then we draw the rectangle filling out the rest of the curve, or of the interval. So this is the approximation of you just using that specific interval. Okay, so if you do this for every single interval of length 1 over n, we got this formula from last time, that our first rectangle just starts at 0 and stops at 1 over n, which is a boring one, and then you continue. So we have f of 0 plus f of 1 over n, and we stop, remember, not at 1, but at 1 right before. So that's where we stop. So that's where we stop at f of n minus 1 over n. That would be this here. This is f of n minus 1 over n. Okay, so again, why is the w outside? Because we factored it out from all the expressions of area. So we got to this point where we got, after simplifying, right, when you plug in 1 over n, you get 1 over n squared. When you plug in 2 over n, you get 2 over n squared, etc. So all these terms have a n squared, 1 over n squared common factor, and then we get the sum of squares. So last time we established a formula for that. The sum of squares is n times n plus 1 times 2n plus 1 over 6. It's a very handy formula because now we have a nice expression of the area of a left rectangle approximation just in terms of n. So for example, if you want to know what the left, so remember this is just for, not in general, but this is for y equals x squared from 0 to 1. It's not a universal approximation. So for example, if you want to do, if you want to find L, let's say for some reason you want to have 11 equally spaced rectangles, or then you just plug in 11 into n. So 1 over 11 cubed, and then 11, 11 plus 1, 2 times 11 plus 1 over 6. That would give you, the estimation of the area using 11 rectangles, for example. Okay, so now what we can do is we can see, okay, what happens if we increase the number of rectangles up to infinity? Let's see what happens there. So, so I'm going to rewrite ln. ln we found was 1 over n cubed, and n 2n plus 1, n plus 1 over 6. So we have the n's cancel, and if we distribute, we have 2n squared plus 3n plus 1 over 6n squared. So this is L of n for any number of rectangles. Okay, so now if we take the limit as n goes to infinity, we establish that taking the limit, or if you increase rectangles, you decrease the error. So you would think that whatever this limit is going to be pretty close to the actual area. And we'll find out that it has to be the exact area. We found out it was 1/3. Okay, so let's think about what we can do with this left approximation. All right, so let's look at our curve again. So that was for last time. Let's look at our curve. And let's take a random interval in between. And let's establish again xi plus 1. Okay, we just had said before that if you want to take a left approximation, you draw your height of the rectangle on xi and then draw over. So this is your approximation on this interval. Now, where do you draw the rectangle for right approximation? What point in the interval do you draw for right approximation? Yeah, xi plus 1. So let's draw that one. Draw it over, down. Okay. Now, what's the actual area? Is this stuff in between. This is the actual area. Okay, would you agree that for all intervals, we're going to establish this later, but for right now we can just look at the picture. For all intervals in 0, 1, the left approximation of the interval is always in between the actual area and the right approximation. Do you get the right is bigger in area than the actual, and the left is smaller in area than the actual? Would you agree with that? So this is actual. Does that make sense? So you can draw that. You can draw this picture for any interval you want inside. Now it'll always have this inequality. Is that okay? Okay, I'm going to assume it's okay. All right, so the idea is, if this is true always, that whenever I take a left approximation and a right approximation for this specific interval, we'll generalize this, that the left for a specific n is always going to be less than the actual area, and the right for a specific n will always be greater than the actual area. So what happens if we take the limit as n goes to infinity of both the left and the right approximation? What would be interesting if we compared the left and the right? What do you think would be interesting? If what happened? Yeah, if they're equal, what could you say about A if they're equal? Yes, that's exactly it. That if the limit of the left bound is equal to the limit of the right bound, then A is actually equal to the shared value. So that'd be cool. So we don't know that explicitly right now. We'll prove that later, but uh, we don't know in general yet that this is enough. It turns out that just one of the limits is fine, and it'll always equal the right. But if we calculate the right limit and find that it's also one-third, then we'll know for sure that the actual area is one-third. So let's do the right approximation, and then let's see how we can maybe generalize this statement. Okay, so remember that the area is always going to have this form. Your width, and then times L1, L2, for any type of approximation you have, if you want to keep width uniform, is always of this form. So now our goal is just to figure out what W and all these L's are. So our W is the same, right? It's using left or right approximation, your widths are going to be the same. But what differs is your L's. Okay, so someone tell me the first L in a right approximation. So if this is 0 and this is 1 over n, what is L1? Where do you define the height of your first rectangle? So recall that in left approximation, your first rectangle was at 0. So where do you draw your first rectangle for right approximation? Okay, if you want to start from the end, you could say f of 1. That is a rectangle you have. That is true. If I want to start from the beginning of the interval, which would it be in this interval here? That is true. That is a rectangle that we have. Let's say that's the last one. Yeah, you draw the rectangle at 1 over n. Okay, so we have f of 1 over n. So all that really matters for left and right is just to know how to distinguish between the first and the last rectangle, because the rest you just add 1 over n. So you just keep on going, and then right before 1, what is the f right before 1? What goes here? So what's this one? What's that one here? It's an expression of n. Do you remember what that looks like? So I keep on adding 1 over n, and then I get f of 1, what comes right before it. Give me 2 answers. Good, yeah, n minus 1 over n. Or I can think of it as 1 minus 1 over n, and then that, if you do a common denominator, that's n minus 1 over n. Okay, so now let's calculate that. So we did this from left approximation. It's 1 over n squared plus 2 over n squared. And then we have n minus 1 over n squared. All this is the same except for we have a plus 1 over here. Okay, so what is that? We have 1 over n squared, plus 2 squared over n squared. We have n minus 1 squared over n squared, and plus 1. Okay, so big question. How do you is there a term you can factor out in the parentheses? And if not, can you make it so? What term do you want to factor out, first of all? Yeah, you want to factor out a 1 over n squared. So let's just do it. Okay, so you factor out 1 over n squared, you get 1 plus 2 squared up to n minus 1 squared. Now what happens if you factor out a 1 over n squared from 1? What happens when you factor out a term that is not a factor? How do you deal with that? Like for example, if I have a plus b, and then I factor out an a, what goes here? Or that's probably not, why don't we do it like this? If you have 1 over a plus b, and you factor out a 1 over a, what goes here? Like what would need to be here in order to get b? Yeah, so it would be n squared here. So in this case, it would need to be ab. So just notice that when you're factoring, it's essentially the same as multiplying or dividing. Essentially, you're dividing every term by 1 over n squared. So that's kind of like multiplying everything by n squared. Okay. So now this is the formula we have, right? It's n plus 1, 2n plus 1 over 6. And this is 1 over n cubed. Oh, actually, by the way, I think yeah, so here, sorry, I made a little bit of a mistake. So notice it goes up to n minus 1. So I was thinking ahead to right approximation. But you obviously get the same thing. But it's 1 over n cubed, and then you plug in n minus 1 for all these things. So it's n minus 1, n, and then 2, n minus 1 plus 1. Okay, so it's n minus 1. Yeah, sorry about that. But as we can see, it's not a big deal. So will this be 2n minus 1? So this limit also goes to 1/3. Anyway, all right, so what we have here, this was actually the one we did in the beginning. This limit is 1/3. Okay. All right, so any questions on the left and right approximation there? Okay, so what does this mean? Is that we have that that L of n was less than or equal to A was less than or equal to R of n on 0, 1 for y equals x squared. And we just showed that as n goes to infinity, that L of n goes to 1/3, and R of n goes to 1/3. So the area is 1/3. So we're done. Okay, cool. So the what we're going to try to establish today is that we don't need to do this every single time, that we don't need to check the left and the right. We'll show that it's enough just to do the left. But it's good practice for right now, the left or the right. Okay, so that's kind of the big kicker here. Okay, so let's talk about that. Okay, let's say we're on an interval AB. Let's suppose that suppose f of x is always increasing or always decreasing. On the interval. And we'll say why later, why we need this to establish this. Okay, what is the formula for ln? And what is the formula for Rn? Can someone say, so it's W, L1, L2, etc. And this is W, and then some other L's. So let's do ln. What's W on the interval AB? What do I want my widths to be? So it's not going to be 1 over n in this case, but if I look at the interval AB, how do we determine W from that? Do you remember what W means? There's a formula for W. If you don't remember, you can make it up. Yeah, it's B minus A, well, over n, right? B minus A over n. That's fine. So if you forget that, just remember that what is B minus A? B minus A is the length of the interval. And dividing by n divides into n parts. That's what division is, right? It's dividing something into n equal parts. So that's exactly what this means, right? B minus A over n just means you take the length of the interval and then you cut it up into n pieces. So each piece is B minus A over n. Okay, cool. So let's do the L's. So on an arbitrary interval AB, which is your first length interval? Or what's your first length of your rectangle? So here's AB, and the point after here is A plus B minus A over n. So what's your first F? F of A, yes. And then what's your next F? We can keep this as W for now. You can do it in terms of W if you don't want to do B minus A over N. Yeah, so in terms of W, it's just A plus W. And then where do you stop? What's the last rectangle? How big is the last rectangle? So we can just call this one B minus W. So what would the last rectangle be? B minus W, right? You do left and right approximation, there's not many choices. Right? It's either the first part of the interval or the last part of the interval. So B minus W is the last one. So it's the big distinguisher between left and right. It's just where do you start and where do you end? And they're going to be different for both. So speaking of which, where do you start for your right approximation? Which F do you start with? A plus W, yeah. And then where do you end? You end at B. All right, so this is a general formula for the left and right approximation of any interval. Increasing and decreasing, that will come later. Okay, so what happens if you do this? Let's do let's do R minus L. What happens if we subtract R and L? What terms go away? What term does not go away? Think about subtracting these two things. Can you give me an example of a term that does cancel? Yeah, f of a and f of b stay. So since I'm doing r minus l, f of b will be the positive one, and f of a is the negative one. And then this is all multiplied by w. So all these other terms disappear, right? Here's an f of a plus w. F of a plus w is I'm subtracting. So everything is going to go away. And the only things that stay are f of b and f of a. So now let's bring back what w is. Okay, so why do that is that what is the limit as n goes to infinity? And to think that, really say, what is f of b minus f of a, and what is b minus a? And if you take n to infinity, what do you think happens? First of all, As n goes to infinity, does a, b, f of a change? Do those values change? Would they? Those are just the endpoints, right? You see? N, yeah, n doesn't matter, right? N could be whatever it wants to be, but a, b, f of a will never change. So this is going to go to 0, right? You see that? You have a number divided by n, and n goes to infinity, right? These are fixed. B, A, f of A are all fixed. So it's really like this. A limit as n goes to infinity of c, where c is equal to b minus a times f of b minus f of a. So one thing you do have to worry about is f of b equal to f of a? Right, that would give you a 0 over 0, and that would be bad, right? Can you say why it's not true? Yeah, so look at the graph and look at the givens. Which part of the given tells you that the endpoints can't be equal? These are the givens. Yeah, it's always increasing or decreasing, since f is always increasing or decreasing. So we don't have to worry about any 0 over 0 nonsense. And of course, b is not going to be equal to a. So yeah, that's it. So what does that mean? Does that mean that means the limit from the left equals the limit from the right? If the limit of their difference is 0, that means the left and right approximations are always going to be the same whenever you're on a always increasing and always decreasing interval. Or does that make sense? If the limit of the difference is 0, that means the limits are equal. All right, since this is 0, that means the two things must be the same. Okay, so any questions on that? So what does this mean is that, so let's kind of establish how we can use this to actually find area, because actual area isn't anywhere here yet. So let's see how area actually plays a role. So left approximation versus area versus right approximation. Okay, so here's where we're going to bring in the increasing and decreasing. Let f of x be increasing on AB. Then L of n is between the area and R of n. Okay, so let's see why this is true. So let's say xi and xi plus 1. Let this be any width interval. Okay, so just as a picture, here's increasing graph from A to B, and here's a width interval xi plus 1. Okay, so let's see how the area will play a role. So what is the left approximation of this interval? How do you it's an actual value you can describe. What would the value be? So you need a length and a width, right, to describe a left approximation. It's a rectangle. So all you need is give the width and then give the length. And remember, we're looking at this interval here. So I've asked this probably a bunch of times, but it's important to keep asking it because it's how you can really establish what's going on. Yeah, the width, well, it would be xi plus 1 minus xi. Or we can just call that w. So that would be your w. And yes, length is f of xi. Okay, so would you agree that f of xi is less than or equal to f of x on the interval? Do you agree with that? Good. Okay. Now, do you agree with this? So here's something in general. If g of x is less than or equal to h of x on an interval, then the area underneath g and the area underneath g of x is less than the area underneath h of x. Do you agree with that? It's nothing too absurd. So here's g. Oh wait, g is smaller. Well, here's h. Here's h and here's g, let's say. So it's always less than or equal to h. Do you agree that the area underneath g is less than the area underneath h? Yeah, it's pretty natural. Nothing too absurd. So here's g, and area underneath h is everything else. Is all of g plus a little bit extra stuff. Okay, so that means that if f of xi is less than f of x on the interval, then, so if this is the area of left approximation, this has to be less than the area of the actual, right? Because what is f of xi? This is like the function y equals f of xi. the horizontal line. Here's the line f of xi. And I'm finding the area underneath f of xi. So that's essentially what you're doing when you're doing left approximation. So the area under y equals f of xi from xi to xi plus 1 is exactly left approximation. So do you see the two functions here are f, which is the curvy function, and then y equals f of xi. Does that make sense? So I'm trying to compare like this approximation case to this kind of obvious case here. Because f is increasing, that means that obviously it's going to be bigger than the function y equals f of xi on that interval. Am I making sense? Great. So remember the key part was increasing, right? I could not say this if this wasn't increasing, because if it ever dipped down, then the left approximation may not be underneath the curve, right? So it has to be always increasing. Okay, cool. So now let's see it from the right. So we just established that left approximation on an increasing interval is always underneath the curve. Now let's do right. So what is the area of your right approximation? So you have w, and then what's your length? Yes, f of xi plus 1. This is your w, and this is your length. Okay, so now we look at the function. Look at the function y equals f of xi plus 1. So this is a function, still horizontal line. Now, do you agree that f of x of y equals f of xi plus 1 is greater than f of x on this interval? Do you see why? Yes, because it's increasing. F of x of I plus 1 is the biggest point in the interval. So that means it has to be the largest. So this is always bigger than the area. So we just established that, in general, on increasing intervals, L of n is always less than A of n, or A, which is always less than R of n. Oops. All right. Okay, so and remember what we had before. Let's see, where was it? Right, before we showed that the limit of left approximation, right approximation is always the same. Oh, I think I lost it. Yeah, on increasing intervals. L of n A less than R of n. And we showed that the limit of L of n to infinity of L of n is equal to the limit of n goes to infinity of R of n. So, so if we just find L of n, this is the area. So it's like saying on intervals. So, and then if we do the same thing for decreasing, and then this will allow us just to say, okay, we can just forego about increasing, decreasing, because if we do this just for left, regardless of how the function is changing, we can find the actual area. So let's quickly just do it for decreasing, and then just see how it's different. Okay, so for decreasing, the area is going to be the same. It's going to be xi plus 1 minus xi, and then times f of xi. Okay, so is this bigger or smaller than the area? The actual area. First of all, f of xi is bigger than f of x. Do you agree? So that means this must be bigger than the area. Right? If it's decreasing, then the left becomes bigger. But if for right approximation, it's going to be smaller, because this f of xi plus 1 is smaller than the function. So on decreasing intervals, it's R of n that's smaller. We also showed that its limit as n goes to infinity of R of n is equal to the limit as of L of n. Then you can just choose one, it's the same. Okay, so why do all this is to say that because we established that if we split the domain up into increasing and decreasing, it's guaranteed that we have left approximation and right approximation are its bounds, and that the limits will agree with each other and are the actual area. So since we approve this really for all possible types of intervals, that means we don't have to do it ever again. A is just always going to equal to, that's it, and we're done. And again, this is also equal to the limit of R of n, but the whole point is that you can just choose whichever one you like best. Maybe it'll be easier to write the formula for L of n in some cases, sometimes it's easier to write the formula for R of n, but that's it. Okay, so before we stop for a break, I just want to, we can even go further into our theory that left and right aren't the only choices of approximation we can do. But we want to say that really it does not matter how you draw your rectangles, that the area will always be the same. Okay, so let's see what I'm saying about that. Okay, so we draw, let's draw a little bit more interesting. Okay, so here's your left approximation. And here's your right approximation. Okay, so do you agree that this is true? That, let's suppose you pick some point inside. Let's call it xi star for some reason. And let's instead draw the rectangle from here. So we go up to the curve, and that defines the height of a rectangle. So that would be the area of the rectangle. Notice that we don't know if this is an under or over approximation. Do you see why? Because there's, yeah, let's see what, yeah, it's both, right? Sometimes there's stuff that's over, but there's also stuff that's under that doesn't get taken account for. So we don't know, right? We don't know which area is bigger. However, what do we know? I mean, if you just look at the picture, how can you compare this middle rectangle to L and R? Do you agree that it's bigger than L and smaller than R? Yeah, somewhere in between. So this is, and then it's because this is an increasing interval. Since f of xi is less than f of xi star is less than f of xi plus 1, that means these areas must be in the same order. That is ln is less than, we'll call this Sn for a reason, less than Rn. So, okay, so what is Sn? Let Sn be the area approximation using arbitrary lengths. Lengths inside the rectangles. The width rectangles. So, and no matter where you, so maybe like on the next interval, you could put it like, let's say even over here. It doesn't even have to be the same place every single time, relative. It could be like way over here. But no matter where you put it, right, it's always going to be somewhere in between L and R. Does that make sense? Like, I don't even have to be consistent in about like where I place this kind of middle line. It's always going to be in between. So what does this mean? We just showed that L is equal to R. But as the limits, as n goes to infinity, of L of n is equal to R of n. That's kind of the whole point of this whole discussion. So Well, if S of n is sandwiched in between, that means that S of n is also the actual area. So what is the conclusion? That it doesn't matter where you put your rectangles. If you have a even length, it's all 1 over n. We'll even be able to generalize that even more. But all that's necessary is that you just draw rectangles wherever you want, and then take the number of rectangles to infinity. All right, so let's take a 5-minute break. But I'll just say, what are these xi stars? Xi stars is going to be called the sample point. Sample point for interval xi plus 1. So it just means where you draw your rectangle. So again, does that make sense? Since we showed that if it's increasing, and you can do the same for decreasing, that the left approximation is always the smallest approximation you can make, and the right approximation is always the biggest approximation you take. So anything that's in between is going to be in between. So as you go to infinity, if the smallest and the biggest become the same, obviously that means the stuff that's sandwiched inside, also this is also a squeeze theorem, must also limit to the same answer as actual area. But of course, in actual practice, you might want to use left or right because it's easy to come up with like a formula, right, to actually take a limit of. Where the sample point might be harder to do. Midpoint is a common one that people use. Actually, it's very, very practical if you're doing actual area and you don't really have a function to work with, but you can actually calculate maybe the heights. Midpoint will turn out to be like a very accurate method, more so than left and right. Like it gets closer to the actual answer. Like you don't need to go too far up for large number of rectangles to get pretty close to the answer. Okay, so let's take a break until say 8:38, and then we can continue. All right. All right, we just had a question about for the recording about symmetry. So I'll pause the video here. Look at that. That's a little rundown of what symmetry means. Okay, so before the break, we talked about, so what is area? Okay, so essentially what we just showed was that we can define the area underneath the curve now. Area under the curve. And I'm going to say using uniform length. Later we'll even, uniform width rather. Later we'll even allow ourselves to change the width. But right now using different lengths is good enough. So area underneath the curve is the limit as n goes to infinity of, we'll say w, and then I'll use a different symbol. But f of x1 star, so this is that sample point thing. F of x2 star. So this we just showed before, that if you take all of these rectangles, no matter where you draw your lengths, that it's going to be the actual area. So remember this, and then w was, I'm just going to give it a symbol, because we're going to use a symbol later, but we're going to call it delta x. And that suggests like maybe the derivative was involved, right? That looks like something we did with differentials. And it is true. The derivative will play a role here. Okay, so for the rest of class, we're kind of going to go over making this look nicer. It's kind of a hassle to keep on writing plus, plus, plus all the time, dot, dot, dots. So we're going to turn this into a nice condensed little form. All right, so this is called sigma notation for sums. So I'm going to put in parentheses finite. In Calc 2, you'll talk more about infinite sums, but first you need to know finite, because infinite sums is dependent on finite sums. But some things you can do in finite sums that you can't do in infinite sums, like just because like infinity is strange. Okay, so let's look at that previous long sum. We had f of x1 star plus f of x2 star plus f of xn star. So this is kind of messy. Right, but notice there's a lot of things that are the same in this, on all these terms, right? What's the only thing that's changing within all these terms? It's these little subscripts, right? It's the only thing that's changing. Everything else is staying the same. So we're going to introduce a new notation to be able to turn this whole sum into one expression. So this is what it's going to be, and then we'll explain, every single part of the symbol. Okay, so that's what this is going to be equal to. And then let's explain really what all these things mean. So I'm gonna I'll do a new page and just do in general what the sigma notation is. Okay, so the big thing here is this I thing. All right, so what is this I? I is called the index. Index. So essentially what the index is saying is a way to organize or identify elements in a set. So essentially, like enumerating a set. Okay, we'll see what this set is. The set of elements is going to be related to this fi thing, but we'll kind of explain that. So now, how does I relate to this equals 1 and this n? So these terms define for you what the indexing set is. Indexing set. So really it is just the set of indexing, indices. Set of indices. The plural of index. So it's just how many indices you have, how many elements in the set are there, and what indices and how the indices are enumerating them. Okay, so how do you determine the set of indices from this equals 1 and n? So what does the I equals 1 mean? This means the start of your index. And this I equals n is called the end of the index. End of the index. Okay, so what is the index? Index, so it's a set of integers in this case. So what is the start of the set? Well, it's I equals 1 in this case. What's the next element in the index? It's always going to be over integers. Where the next element after is plus 1 from before. Then you keep on plussing 1. And then you keep on going until you reach the end of the index, n. Okay. Okay, so a lot of, sets and stuff. Let's just kind of see if we can identify the indexing set for a certain sum. So right now we don't really know how the index set is being used, but this is just a definition. Let's do an example. What is the indexing set of this sum? We don't know all the things yet. I don't know what this f of I thing is yet, but can someone list out the indexing set? So what's the first thing in the indexing set? Yeah, so this one was just, for example, 1, but you just start wherever the number is, -3. Then what would the one after be? What's the next one? Yep, -2, -1, 0, 1, 2, 3, 4. Okay, so that's what indexing set is. So again, we have not established what you do with this thing, but we just need to establish, what it is, or how to identify it. Okay, so now, what do you do with it? What do you do with the index set? Okay, so what you do, it's like an algorithm. So I always try to do the code version. It's like a for loop. So in coding, there's this thing called a for loop. let's see if I remember how to write it. 4, and then you have I equals the starting index. And then what do you do every time you do your loop? Or sorry, and it's always going to be in between the start and the ending index. And whenever you loop, you're going to add 1 to I. That's just the coding symbol for all that. And then, so what do you do in every single iteration is that you plug in I into F. Let's say F of X. So what do you do? Maybe, and then, so you plug I into F of X, and then add it to the set, or take the sum rather, and then take the sum. So in the first case, there's nothing to sum with, but in the next iteration, you would add 1 to I and then plug it into F, and then add it to what's ever in there before. So what does this mean is that, so let's do this one up here. So what this is saying is that, okay, look at the beginning entry. Oh, it's -3, right? So look at this beginning entry, which is -3. So this algorithm says, okay, take I equals -3 and plug it into F. Okay, so there's nothing to sum, so we skip that part. Now let's repeat the loop. So once we repeat the loop, we add 1 to I, and then do the algorithm again. So you add 1 to I, and then plug that new I into F. That's -2. And then keep on doing it. That's what this means. When do you stop? You stop at the ending index. I mean, there's only a couple terms here, so I can write out everything. So then F of -1, and then F of 0, and then F of 1, F of 2, F of 3, and we stop at F of 4, because that's the end of the area index. So you start at F of -3, you keep on adding 1 and plugging it in, and then you end at F of 4. So what is this F of I? F of I is a function with variable I. So if you're uncomfortable with all this like indexing stuff, the best way to think about it is that I is a variable. You plug things into I. That's what the index is the things that you plug into I. And then what does the algorithm do? You keep on adding the subsequent terms together, and then where do you stop? You stop at the number at the top of the sum. So you don't have to do integers. You can start from like maybe say I equals 0.5, and you could probably define some weird way I know there's other symbols for it, but they're like rarely used. Other ways you can identify how you iterate. You can iterate by maybe fractional values, but if none of that is described, it's always adding one. So I mean, your starting and ending index could be something different, but unless otherwise specified, it's always going to be adding one. Yeah, but usually they'll be integers. Usually by a way you can like adjust the index to make it always make it integers. Maybe you'll have to do something with the function in order to deal with that. Okay, so let's think about like these f things. So, for example, like not all sums can be made into this nice form. Not all sums can be expressed this way. Maybe if you're very crafty, you can. We'll put in parentheses easily. For example, like 1 plus radical 2 plus pi plus e plus cube root of 5. It's going to be a very weird function, unless you want to be like do a piecewise function, which would be not very fun, to describe all these things of f of I. So for example, like this would be f of 1, like f of 2. But coming up with a function that does that is probably going to be a lot harder than just writing it down. So we probably can't write this as a sum. Probably can't do it. So the whole point of the sigma notation is to put something that kind of looks pretty uniform, like they're all values of functions. So for example, let's do this one. Let's just do a boring one. 1 plus 2 plus 3 plus 4 plus 5. What's the function here? Can you, is there a function that has integer values with all these? Like what function, what is f of x? Yeah, f of x is equal to x. Can you think of another one? So if you have f of x equals x, what's your index? What would the index for this first one be? What would your starting index be? Yeah, I equals 1. Can you think of another function that if you plug it in, it also works? So the hint is you might need, can you try using a different index and then figure out the function? So don't start from 1. You start from another integer and then come up with the function. Yeah. What if it was f of x minus 3? F of x equals x minus 3. Yeah, then you would start at I equals 4. So it's really a combination of the index and the function. These can describe the same things, which if you write them in the sum form, you may not see that right away. You have to like think more about it. So notice that these two things are the same. So you see I equals 1 to n of f of I is equal to I equals 4 and then I minus 3. What would the ending index be if you stopped at n here, what would the index be? Where would you need to stop? What would this I be? Good, yeah, n minus 3. Okay. Yeah, so just be aware that the sums are not unique, right? You can adjust the function, f of I, and the index to make two sums the same. So these two things give the same value. Do you remember what the value is? We proved this. Do you remember what that was? If you don't, it's fine. It's a good one to know. It's n times n plus 1 over 2. Okay, just one more thing. Can you say why this is also a fair sum? Why is this also the same thing? So all these three things are the same. Yeah, you just plug in 0 and you get 0. So who cares? Yeah, so yeah, just be aware that sometimes starting from 0, right, nothing happens, right, because it's just maybe just equal to 0. So if anything's equal to 0, you could just ignore it. You can run the sum, you can add it to the sum. Yeah, so let's do some examples. I equals 1 to 7 of I squared. So our function is I squared. So first you plug in 1, you get 1. Then you plug in 2, you get 2 squared. Then 3 squared, up to 7 squared. So we did this formula. We figured out that this was right, n plus 1, 2n plus 1 over 6. So it is going to be 7 plus 1, 14 plus 1. So whatever that is, 7 times 8 times 15 over 6. Okay. Okay, so is everyone comfortable with what everything means in the sum expression? So the sigma just means you're summing something. This is your function of I. This is your starting value in the index. And this is your ending value. Okay, someone do this one for me. What's that? The sum from I equals -1 to 5 of 2. What's that? So what's my function? What's f of I? Is there a function? What do you think? Well, what do you think it would be, right? It's whatever goes here, right? This should be your f of I. So that's what it is, it's 2. Okay, so let's do our loop. What happens when you plug in -1 into 2? When you plug I equals -1 into the function 2, what do you get? Well, you get something, right? You get 2, right? It's the constant function 2. Right? What happens when you plug in 0? Exactly. Also 2. What happens when you plug in 1? Well, you get 2 again. It's 1, then 2, 3, 4, 5. Yeah, so don't be afraid if you don't see an I. That just means it's easy. So is that 1, 2, 3, 4, 5, 6, 7, 7 times 2. Yeah, so in general, if you have the sum, so I made it hard by using a negative in there, but something that's generally true is that the sum from I, now it's important where you start from, equals 1 to n of A is equal to NA. Because you're just adding A up n times. Now, what happens when you start from I equals 0? If you start from I equals 0 to n, what do you get? Well, NA is I equals 1, right? Do you agree that here? Would you agree this is true? If you plug in I equals 0 and then you do, or let's see this. Actually, let's express it like this. Would you agree that this is true? You can split up a sum this way. Yeah. Does that make sense? Like, I'm just taking out the 0th term. So this one was NA. And then what happens when you plug in 0? A. So how many A's are there? If you factor out an A, you get n plus 1. Yeah, so the big lesson here is index really matters. Sometimes it doesn't, where maybe 0 doesn't really do anything to the sum, right? Because when you plug in 0, you get 0. So it doesn't do anything. However, when working with something where 0 does give you something, in this case this constant function just gives you a back, you have to consider that. Right, because you can think of also how many numbers are in between 0 and n, actually n plus 1 of them, because you have to include 0. Okay, so let's do some properties of sums, and then we'll finish. Properties of finite sums. So to remember properties of sums, just remember properties of like normal sums. So for now, I'm just going to always start from I equals 1 to n. And let's say I have AF of I. What do you think this is going to be? What do you imagine this would be, just based on what you know about sums? Or if not, say, like, how do you expand this? Like, term by term. So what happens when you plug in 1? You get AF of 1. And then you get AF of 2. And where do you stop? AF of n. Okay, so what can you do in the sum? Can you do something? Can you maybe factor? What can you factor from all these terms? There's an a in all of them, right? So this is going to be a times f of 1 plus f of 2 all the way to f of n. But what is that? Sorry, what is f of 1 plus f of 2 all the way up to f of n? That's a sum, yeah. So this is equal to a times the sum from I equals 1, same index, to n of f of I. So what does this mean is that things without a's can be factored out. Things without i's can be factored. Sorry, that's a little laggy right now. Does that make sense? So a has no i's in it, so that means you can just take it outside. It's just factoring, that's all it is. It's kind of the distributive property. All right, here's another rule, property. If I have the sum of two functions in a sum, so I'll just do it out just for the sake of time. We have f of 1 plus g of 1 plus f of 2 plus g of 2. I'm just going down the line of the index. And keep on doing this until we get f of n, g of n, plus g of n. So now we can use, this is just a normal sum. Now we can use the commutative property of addition and write it this way, f of 1 plus f of 2 all the way to f of n plus g of 1, g of 2, all the way up to g of n, right? Nothing, I didn't change anything. So this is a sum of f's, and this is a sum of g's. So this is kind of like a distributive property of the summation sign, that you can distribute the summation sign over addition. pretty reasonable, right? There's nothing too absurd here. Okay, but here's the one thing you can't do. Can't really work with products as well. So let's just say what this would be. So let's first of all, this is not equal to just the sum of the product. And we know this is not true just based on normal sums. Right? We have a foiling property, right? This is pretty much FOIL. So if you write it out, this would imply you just multiply everything across, right? But with FOIL, there's a distribution going on. So this is the FOIL for sums. And notice I'm keeping the same index. Like they're both up to n. If that wasn't true, then we'd have to do something. So I can just do normal distribution and have this as f of 1 sum of g of I plus f of 2 sum g of I, and then all the way to, I'm going to actually change this to m because it's okay. And f of m sum gi. But notice now that we have all these things that are the same, all of these sums gi, sum gi, sum gi, and we have all of these things that are changing by a simple index, right? So now we have something changing, and then we have something that's not changing in I. So let's turn this into a different index. Let's introduce a new index called, like, say j. That will run from 1, and where does it end? At m. And this will be a sum of fj, and then you do the sum of the gi's. Okay, now we can use the constant rule. Right, notice the constant rule says that if we don't have something in terms of I, we can take it out, or we can put it in. So do you agree that fj is not something of I? There's no i's here. It's a different thing altogether. This has no relation to the i's in the g terms. So we can just bring that inside. So this is a double sum. There's two sums going on. J is going from 1 to m, and G is also going from 1 to n. So we use different indices to determine different sums. So this is the FOIL formula for a product of sums. We'll never use that, but it's kind of a cool thing to know. My first introduction to a double sum. So what you think of this is like a double for loop. You start, you do for, so if you're computer people, it'd be j equals 1, j less than or equal to m, and then j plus plus, and then you do another for loop in terms of the i's. So notice that j comes first because it's the outermost. And then you do the sum. fj, you add fjgi. So you run through all the j's first. So whenever you do this inner for loop, the f is going to be the same. So it's going to be like, for example, f of 1, g of 1, plus f of 1, g of 2, and then all the way up to f of m, no, f of 1, g of n. So that takes care of the first j. And then you do j plus 1. So j plus, then plug in 2, and then run through all the i's. You see like what the double loop is doing? Sorry, my pen is being a little slow. Everyone see that? And then you go all the way to f. It's a little weird, but if you just kind of go slowly through it, you get all of them. So there's two sums going on. So that's why I use different letters to denote the two things changing. Okay, but we'll probably may rarely see that, but you might see another class, and kind of good to kind of think about. And it just says, you know, how do you deal with products of sums? And you can kind of do this for small cases just to like prove to yourself that it works. Like do this, like 1 plus 2 plus 3 plus 4 plus 5, and then multiply this by, I don't know, 6 plus 7 plus 8 plus 9 plus 10. Like, do this out normally, like without adding them up, but like do the distribution, and then express this as a sum, and then see if you get the same thing as this formula, because it should be. Yeah, so this is the generalized FOIL formula, which is pretty cool. Okay, yeah, so sorry, a little bit over. But so your quiz is on Wednesday. So studying for that, and it will be you'll have the whole class period to do it. All right, but I can stick around for questions if you have them.